In this video, we're going to look at some examples of how to determine whether a molecule is polar or nonpolar. So in order for a molecule to be polar, we're looking for it to satisfy two criteria. The first is that it must contain polar bonds. And there's some gray area here, but the cutoff that we're going to use in this course is if the electronegativity difference between two atoms connected by a covalent bond is greater than 0.4, then we'll call that a polar bond. And the second thing that we need is that the polar bonds need to be arranged around the central atom in an unsymmetrical manner. So it can't be symmetrical. So let's look at a couple of examples. So before we look at some actual molecules, some ideas of what we mean by the bonds being arranged in a symmetrical or non-symmetrical manner, we've got some diagrams here. Right? So if I have two bonded atoms, and they're arranged in a linear relationship about the central atom, and the two terminal atoms are the same, then essentially their pull on the electrons is going to cancel out, and that molecule is going to end up being nonpolar. The same would be true if I have three electronegative atoms arranged around the central atom, and they're in a trigonal planar relationship. Now, an example of a case where the molecule would be polar due to an unsymmetrical arrangement would be an example of a trigonal pyramidal molecule, right? So in this case, we have a tetrahedral electron geometry, but we've got a lone pair up here at the top, and I've got my three bonded atoms are essentially all below the plane that's sort of coming out of the page here, right? And so the net pull on the electrons is going to be in a downward fashion. They're not going to cancel out. This would be an example of a molecule that would have an unsymmetrical shape and would be polar as long as the bonds are polar. Another example would be if I have a bent molecule, either due to a trigonal planar electron geometry with lone pair or tetrahedral with two lone pairs. If I have a tetrahedral arrangement and all of the terminal atoms are the same, that would be another example of a symmetrical relationship where all of the vectors would cancel out. So if we look at a specific example, we want to determine whether the HCN molecule is polar or nonpolar. So the first thing we have to do is determine the Lewis structure. So I'm not going to say this for every molecule, but I encourage you to stop the video, see if you can determine the Lewis structure and the molecular geometry of each molecule, and then restart the video where I'll give the answers. So HCN has this Lewis structure. So I've got two electron groups. So my molecular electron geometry and the molecular geometry is going to be linear in this case. So in order to determine whether the molecule is polar, the two questions I have to ask is, do I have polar bonds? And are the polar bonds arranged unsymmetrically about the central atom? So to determine whether I have polar bonds, I need to look at the electronegativities. So hydrogen and carbon have an electronegativity difference of 0.4. So that's right on the border, but this is one pair of atoms that you want to be sure to remember. I know I made a big deal about this in class. A carbon-hydrogen bond is a non-polar bond. However, the carbon-nitrogen bond has an electronegativity difference of 0.5, so we would consider that to be polar. So going back to the molecule, yes, I do have a polar bond. The carbon-nitrogen bond is polar. And are the polar bonds arranged unsymmetrically about the central atom? Well, I've got the carbon-nitrogen on the right that will not be canceled out by the nonpolar carbon-hydrogen on the left, and so, yes, I have an unsymmetrical arrangement, and so both conditions are met, and HCN is a polar molecule. If we look at another example, I want to determine whether CF4 is polar. So the Lewis structure would look like this. I have four electron groups, no lone pairs, so both the electron geometry and molecular geometry are going to be tetrahedral. So let's go back to our electronegativity chart and see if I have any polar bonds. So a carbon-fluorine bond, electronegativity difference is 1.5, definitely polar. So our first criteria is met. Now the second criteria, are the polar bonds arranged unsymmetrically about the central atom? So I actually want to look at a more accurate model of what this tetrahedral molecule will look like. So if we come down here, this is what our CF4 would look like. So I've got this tetrahedral molecular geometry. All of the atoms are the same, And so, right, these two guys up here are going to be canceled out by these two guys down here. So if I have a tetrahedral molecular geometry and all the atoms are the same, it doesn't matter that they're polar. I have a symmetrical arrangement, and so the pull on the electrons is going to be canceled out. And so if I come back here, we do have polar bonds, but the molecule is symmetric. The polar bonds are arranged symmetrically around the central atom, so I don't meet the second criteria, and so CF4 is nonpolar. Here's a third example. So I've got CH2Cl2. So here's our Lewis structure. I have 4 electron groups, no lone pairs again. So again, I have tetrahedral. So let's see if I have polar bonds or not. So again, carbon-hydrogen, non-polar. But the carbon-chlorine bond is going to be polar. So I do have polar bonds. But to see the second one, let's take a look. I was tetrahedral with the CF4, and it turned out to be nonpolar. But in that case, I had 4 fluorines. Let's see what it looks like. Right? When I've drawn this Lewis structure here, it kind of looks like they'd cancel out. I got the chlorines on opposite sides. I got hydrogens on opposite sides. Remember, the Lewis structure is not actually what the molecule looks like. So you have to be sure to consider the actual molecular geometry and not just what it looks like in the Lewis structure. Because, of course, tetrahedral is not planar like this. And if I come here to my CH2Cl2 molecule, all right, we can see in this case, the atoms, the electronegative atoms, are not symmetrically arranged around the central atom. It doesn't matter where I put the chlorines and the hydrogens, I'm always going to end up with this relationship where I've got 2 hydrogens that end up being on one side of the molecule and 2 chlorines that end up being on the other side of the molecule. So I do have the required unsymmetrical relationship. So in CH2Cl2, I do have polar bonds. They are arranged unsymmetrically about the central atom, so that molecule would be polar. All right, how about PCl5? Here's our Lewis structure. 5 electron groups, no lone pairs. So both the electron and molecular geometries are trigonal pyramidal. So let's answer the first question. Do I have polar bonds? Phosphorus chlorine, 0.9 electronegativity difference. So I do have polar bonds. So answer to that is yes. Let's see what the molecule looks like. So I've got my PCl5 here. And so when I don't have any lone pairs for any of the electron geometries, as long as all the atoms terminal atoms are the same, they're always going to be symmetrical, right? My 3 guys in the equatorial plane kind of look like a trigonal planar molecule. Those are going to cancel out. The 2 molecules on my axis, they'll cancel each other out. So the molecule is symmetric. It's not unsymmetric arrangement. And so I do have polar bonds, but I have a symmetric arrangement of the electronegative atoms around the central atom, and so the molecule will be nonpolar. All right, the second to last example. Here I have BRF3. So here's my Lewis structure. I have 5 electron groups, so the electron geometry will be trigonal bipyramidal, but I've got 2 lone pairs, so the molecular geometry will be T-shaped. Let's check and see if I have any polar bonds. So bromine to fluorine, 1.2 electronegativity difference, so I do have polar bonds. So the first condition is met, and do I have an unsymmetric arrangement? Again, to see that, we need to take a look at what this molecule actually looks like. So the T-shaped molecule, right, it's trigonal bipyramidal, but I've got a lone pair that would be here, and I've got a lone pair that would be here. So the atoms that are remaining, right, these 2 guys will essentially cancel each other out, but there's nobody to cancel this one out. So I do have the required unsymmetrical arrangement. So I have polar bonds. I do have the required unsymmetrical arrangement. So BRF3 would be polar. And one more example. So here I have C3H8. So remember what I said before. When I have carbon-hydrogen bonds, the molecule, or those bonds, are going to be nonpolar. And so doesn't even matter what the Lewis structure is. If I only have carbon and hydrogen, I'm going to have no polar bonds. So the first criteria is not met. Doesn't even matter if it's symmetrical or not. In this case, it's not, but the molecule is nonpolar if it only contains carbon and hydrogen.